We're going to look at this interaction between quantum computing, which, let me say fundamentally, is computing. As much as we want to make it special by sticking this word quantum in front of it, we do a lot of other types of computing. So it's only natural when we think of solving particular problems to throw this into the mix, just as we throw GPUs into the mix, large and small classical systems, and so forth. But there is a lot of talk, though, about this combination. And before we get going, I'm not going to ask you for any statements on this topic. We're just going to run down. We know your names, but maybe just a little bit more background on yourselves. So who are you, where are you from, and why are you sitting here? Okay.
Should I start?
Steve?
Okay,
Yeah.
great. Steve Brierley, CEO of Riverlane. So Riverlane, we are helping companies solve quantum error correction. I mean, error correction is really the big challenge to unlock utility scale quantum computing, and it's a classical compute problem. So it's a real-time data processing problem. And so it's a natural place to integrate with HPC, and so indeed we work with companies building quantum computers, two of which you have here, and with places like Oak Ridge National Labs.
All right, yeah. I present IQM, which is a company that builds full-stack quantum computers based on superconducting approach. And what we really focus on is actually bringing those systems into HPC centers, and this is the core part of our business. And we have been selling now around the world. We're very happy also to get one system into Oak Ridge and then work on the integration, not only in HPC, but also the error correction. And I'm really excited about this topic, yeah.
So coming from Oak Ridge National Laboratory, I'm sure few people would be surprised that we think high-performance computing is one of the most transformative and pivotal capabilities that we have. And very much like you were saying, Bob, this distinction between quantum computing and HPC is something that we're looking to blur, because we see quantum computing as a new capability to be integrated into our computational workflows. And so my personal outlook here is that the better we can converge these paradigms, the more impact that we can have on the Department of Energy's mission for scientific discovery, energy innovation, and national security.
So my name is Alan Ho. I'm the CEO of CoLab. So CoLab is a short for quantum collaboration. And our mission is to collaborate with the semiconductor industry to bring its capabilities towards manufacturing of quantum computers. I'm also part of a larger consortium of companies, including HP Enterprise, Synopsys, Applied Materials, where we believe that quantum computers are actually accelerators for HPC, and that there really isn't any difference between, it's really that quantum computers is a subset of HPC, and that we need to work very closely on making them work together. And I think one of the other aspects to our position is that you actually need HPC to make quantum accelerators work. So that's another aspect that we'd love to discuss in more detail.
And let me just beyond this discussion today, everyone here has great material inside their organizations. Alan, you did a paper with many collaborators, right, including people like HPE. On superconducting quantum computers. John Martinez, of course, represents you, yeah. Lots of times. Steve, there was a blog entry several weeks ago about using GPUs, other types of processors, FPGAs, and so forth when you're actually doing this. So the computing world, and of course, is extremely heterogeneous. It's always been heterogeneous. It's going to continue to be heterogeneous. So this mixture that we're talking about as the insights of our panelists here about how these two will fit together. So even before we get to HPC, right, high performance computing, presumably hard problems, right? Why aren't we just talking about quantum and regular old classical computers, right? You go to one of the hyperscaler data centers, right? You got all these blades out there running all sorts of interesting things in databases. Why are we jumping all the way to HPC and not just looking with quantum with, if you will, run-of-the-mill classical servers? So, Alan?
Well, it really depends on the workloads, right? And actually, one of the things is that HPC has always been on the forefront of computing. And so you actually see this trickle-down effect. A lot of new technologies, they go into supercomputing, which is a subset of HPC, and then it trickles down into everything you talk about. So for example, today, these AI clusters that we talk about, which is quote unquote run-of-the-mill, I mean, that wouldn't have existed if it weren't for someone at Oak Ridge who said, oh, let's bet on GPUs and let's bring GPUs into the data center. This is before they had error correction and the GPUs and all that stuff. So it's very typical that you would see supercomputing in particular adopt a lot of the new accelerators first.
Yeah, if I can build on this, I think that's exactly the essential point. Quantum computers in their current state and quantum processing units, QPUs, we love extending the analogy as far as we can. I think that right now we're trying to find that integration pattern where we can go beyond what we currently do with high performance computing. And just like GPUs in the past were a great accelerator, QPUs themselves can become an accelerator in this paradigm. But the integration there between the quantum processor and the HPC system, the necessity for that, I think, comes from the fact that the quantum computing systems very quickly outpace what we can do on conventional computers. And our HPC becomes the high watermark by which we measure the performance in those systems. So for me, starting with that integration isn't necessarily jumping at the gun, it's kind of addressing the critical issue that when this technology suddenly scales up beyond a certain limit, and that limit's debatable, we will need HPC unquestionably to control it.
Mm-hmm. Yeah?
Yeah, no, I agree. And I think also there is a kind of a clear task in the end for both sides. I mean, there are limitations on the conventional computing. We know that there are very hard problems which they are not going to solve. So there is a need for quantum if we want to get answers to those questions. Mm-hmm. But on the other side, also quantum needs the HPC. I mean, we use the word quantum computer, which might be a bit misleading because there's, for example, no memory in the quantum computer, right? There's unfortunately no quantum memory yet. Maybe there will be at some point. So anyways, we need this part. But also, as we heard, we need other parts to control the quantum computer. So I think we have limitations on both sides. And the nice thing is, and I'm convinced that if you bring those together, actually you have a very perfect fit in the end.
Mm-hmm. Steve?
Yeah, maybe just one point to add. I totally agree with what's been said already. Perhaps the reason is that the supercomputing and the HPC community are used to solving big, impactful problems. And I think when you're looking at a new technology like quantum and it's going to cost billions of dollars, it's very helpful to have a single problem people can point at and say, yeah, I really care about that. I'm already willing to spend a ton of money solving that problem. And hey, if you could go further, I'm super interested in your technology.
Mm-hmm. So Alan, I thought it was video games was where the really interesting things then. Okay. So what are the problems now? So if we look at HPC, we could say these are the sorts of computations, problems we're trying to solve. Do you see quantum as replacing some of the things we're doing in HPC, or do you see it as being more complementary? Because, in fact, when we talk about solutions, I think some people get the idea, here's one computer, you kind of feed it in, and out pops an answer. But in real life, that's not what happens. There are many different processors doing different things, different kinds of processors. Data is entering, data is leaving, data is forked, all sorts of very interesting things. So how do you see them, when we talk about integration? Is it a replacement game, or is it, hey, powerful new tool that complements what we're already doing? So let me start now with Steve.
Sure. Yeah, it's very much a complementary tool. I mean, just to pick one example from AI, large language models basically needed to ingest the entire internet in order to understand how we speak and communicate as humans. If you try to apply AI to areas like drug discovery or the search for new chemistry or new materials, there's just a huge lack of data. And generating new data is incredibly expensive. You have to go into a lab and do some experiments. Quantum computers are very well suited to generating that data. And so that would be one example where quantum computers are used in a very complementary way to classical computers. They're effectively generating the ground truth for some exploration of a molecule space because you're interested in a particular property or particular chemistry.
You know, I agree, and building on this, I think there are different ways then to use the HPC and the quantum computer together, and some approaches which are more well-known are maybe these variational approaches where you do some part on the quantum computer, some on the other computer, and then you optimize around this. And actually there, if you think it through, you don't have very big kind of data flow between the two. You wouldn't actually need an HPC for this one. And what we have been working on now with some of the HPC centers is actually find real examples where you create a problem where there is real workload for the HPC, and then only a subset of this is actually done on a quantum computer. So it's much more kind of native in the way it's implemented. And you find them, we did something in quantum Monte Carlo simulation where most of the stuff is actually done on the HPC and only something on the quantum. Also in the molecular simulation where the VQE is maybe not the most scalable one, we did a different approach. And I think these are the examples, but ultimately I think the big promise of quantum is that it solves you problems that we don't even start today. And we as humans, I think we tend to think in this linear fashion and just do something a little bit better. But I think what we need is also much more creativity in the field and start thinking about problems which maybe we wouldn't even touch otherwise.
And when you add this other element, they're being together and integrated, that gives you the creativity.
Yeah.
You know, there are certain things that come along. I mean, breakthrough is used, you know, people, every week. You can't have a breakthrough every week. But there are occasionally certain things that you can just say, wow, this just opens up, for example, advanced compilation of circuits, right? Or placement of processing and things like this. So the integration will allow this type of thing. So continuing?
Well, certainly at Oak Ridge, we have addressed what is the mission need for building the supercomputers that we have now. And it opens up a whole space of computational challenges. And in fact, there's been a large national program called the Exascale Computing Project that specifically went out and developed application codes that would run on these latest and greatest supercomputers. That is one opportunity to ask, can quantum accelerate our existing code base? Can we find ways to use these integration paradigms to offload tasks to the quantum computer that may increase the time to, or decrease the time to solution, increase the fidelity, many different metrics there. But the part that's most exciting is exactly what we were just talking about, which is that there are whole problem spaces we don't talk about because they were always considered too hard, computationally intractable. We'll never build a machine strong enough to solve them. An example of this in chemistry is known as the Born-Oppenheimer approximation. You decompose your electron and your nuclear degrees of freedom because solving that complex system is too hard. Every code now starts with that approximation by fiat because we assumed historically that we would never get there. Quantum computers completely remove that barrier. So we actually have to go back and start over in our design of applications to explore this new space that was inaccessible previously. Mm-hmm. And I think that's really exciting because we don't know what that scientific frontier looks like.
I think, building along the AI trend, right? So one of the interesting things that we've seen in actually the last several months, especially with GPT-5, what it's shown is that we've pretty much exhausted all the human data, and adding more GPUs and CPUs isn't actually making the AI smarter.
Right.
We've maxed out. Now, the big trend in the future is this thing that, I think Jensen Huang is talking about it, called physical AI, right? And it depends on the scale. Now you have these digital twins where you're doing a lot of robotics and you're doing a lot of simulations and big supercomputers. That's great for very macro things. But the other aspect of physical AI is things at the quantum level, and that's where you need the quantum accelerators. So I think there's a much bigger macro trend on physical AI, which quantum has a very important part to it because it's dealing with the physical sizes that are relevant at the quantum level.
So let's start talking more about the details of integration. And so when we have a vendor like IQM, right, and you talk about integrating one of your systems with an HPC system, what does that actually mean from a hardware? We'll deal with software in a few moments. But so there's a quantum computer, there's an HPC system, right? How do they talk to each other? What has to be done that we're not already doing, right? So what are the issues involved hardware-wise? So Jan.
Yeah, it starts with that these are or have been two different worlds, right? Quantum people and HPC people, they didn't have, let's say on the hardware side, so much interaction. And it started with really very trivial questions like, how big is such a computer? Can they be put on the same floor? What about the vibrations? What about the electromagnetic noise? What are the kind of requirements for the cooling water? Very trivial things, right? And we kind of had to figure all of this out to show it actually works, right? Nowadays, we just bring a quantum computer into an HPC and put it there and it runs. But this was unknown before. We kind of had to test it. And so this is kind of where it starts with. And of course, now the computers that we build today, they have maybe some tens of qubits or so. And they have a physical footprint of a few, let's say 90-inch racks if you would line them all up. So this is what we need today. And of course, then the question is also, how does it scale going forward? What will be the power consumption going forward? And these are not very trivial questions to answer. And this is actually also something where we then do work together with the HPC centers, trying to find out kind of what can they accept on their side and how can we scale our system so that it meets the criteria.
Mm-hmm. Power usage, for example, right?
And then, of course, also maybe just to finish up still on the, like, what is also the physical connection, right? Is it some kind of high bandwidth connections? Do we need this already today? Is an Ethernet cable maybe enough still for today's solution? So it really starts with the basics, and I think we need now to get the basics right, and then, of course, we can think about much more fancy things in the future.
So Travis, at Oak Ridge, I mean, you're certainly known for honest-to-goodness supercomputers, right? It's hard to keep track, you know, what's the best. So I'm sure you can allow a little extra room in the back there for a quantum computer.
So space is a high-priced commodity at Oak Ridge.
Okay.
We're filling it up with everything we can, but the understanding kind of what that footprint looks like, making plans for that, both the power but also the cooling, the operations and the support, the safety. I mean, you can imagine safety is an important criterion. When you start introducing chemicals into your HPC data center, not a lot of people are ready for that yet. So I think having those conversations early on lowers the adoption barrier in the long term, but also mentally gives us a map of how do we scale these things out, how do we prepare for them. In addition to that, there are technical issues about the placement. We know latency may be a major concern going forward, especially as we have interactions between the conventional computers and the quantum computers for error correction or feed-forward circuits. But in addition to that, there's jitter. What happens when the latency itself is moving around? We know that on the HPC side, that can make a big impact on message passing and these types of things. That certainly scales down into the quantum computer. So all of that, we're just at the early stages of understanding.
And it's good to start early, because these aren't necessarily the top level things that most people will think about.
But at the rate which things are progressing, early may just be a few years, maybe 5 years. I think that it'll take us that long to figure it out.
That's right. Alan?
Yeah, I think there's also an aspect of the requirements of using a QPU for accelerating an HPC workload is actually different than using an HPC system to control a quantum accelerator. So when you're kind of talking about, and unfortunately, if you look at, especially in the area of error correction, the throughput, latency, and jitter requirements is all hard. It's all very, very hard, and Riverlane is probably one of at the forefront of looking at that. So I think like that's where the co-design is really needed between the classical hardware components, classical software components, and the actual quantum computing components as well.
And Steve, I'm going to throw in your hardware as well. So for error correction, right? So we think of normal. You've already caught me once. I said run of the mill, so I don't know what normal means now. But regular controlling software, and maybe you have a cryostat or something else, neutral atom cell or something. But now you're also throwing in error correction hardware into the mix as well. So how does that involve the whole integration?
Yeah, and perhaps just to give people a sense of the scale of the challenge. I mean, at utility scale, the amount of data coming out of a quantum computer is going to be on the order of 10 to 100 terabytes per second. So that's like Netflix global streaming. And we have to process that before the next logical operation. Because if you don't, the whole quantum computer stalls. And as Alan was saying, like the jitter also really matters, right? You need to guarantee to send back a signal because the quantum computer is not going to wait. The qubits are going to decohere if you just stop. So there are significant classical compute challenges in implementing error correction at scale. And so we see the way to solve this is to build a dedicated processor, so a dedicated ASIC. In fact, thousands of ASICs all operating together in a parallel system. You need approximately one chip per logical qubit. So I think in this context, this is essentially an additional rack of compute that's sat next to the control electronics and the dilution refrigerator. And so, of course, then you need to couple that with the rest of the HPC stack. And I think from our perspective, we really want to learn a lot from what's already been done in the HPC community. There's a huge amount of knowledge there in integrating different types of compute. And as far as possible, we should either leverage what's already there or certainly learn from it, and hence collaborating with places like Oak Ridge.
So again, the complexity of this integration of very different types of compute in places you wouldn't expect.
If I can add on to that real quick, because I think there's an important issue there, which is the HPC community, and that's an enormous community, has its methods and its workflows and its expectations, and they're not going to push those aside because quantum computing came along. I mean, how many technologies have failed to be adopted because they didn't integrate with the existing ecosystem? So I think these types of experiences, this testing and evaluation, are critical for that reason too.
Yeah.
So software now. Okay, so you've got them connected, you got the bandwidth, all set here. What software are people using to actually run, what I call them, workflows, just to, again, give the idea that they're not all the same thing. What is that looking like today, right? How easy can you orchestrate the types of applications, if you will, across these integrated systems? So Travis, again, I'm going to start with you because you're just so on the ground.
Well, no, I think this is actually an important topic for us. We have a very active research program in this. So I will start off by saying we don't know. That's the right answer. Because the types of access that we have had experience with most recently have been cloud-based access. And there's this notorious issue where I go to get on my HPC system and I get in my queue and I wait for my turn and then I get to run and then I submit my job on the cloud to another queue and I wait in the queue and then I get to run. And so we call this the double queue problem because it's not an efficient allocation of resources. By having a system on site, we can now start to test out this resource scheduling and management problem and make it much more efficient so that we learn what's the patterns for interactions, the pattern for allocation that users expect. And you can only start having that experience once you have physical hardware integrated and you can remove some of the software barriers and firewalls and other types of things needed for that type of research.
Alan?
Yeah, I think the biggest challenge on the algorithm side for integration with HPC is that your typical workload today, we want to use the quantum computer to accelerate just the component that the quantum computer is good at. So taking a problem, a more generalized problem, and then breaking it down just so that you can allocate the part that needs to run in the quantum computer is actually a very, very hard and unsolved problem. Now there was kind of there was a lot of excitement around this variational eigensolvers. This is kind of an algorithm that came out of first DOE and Google did a lot of work on it too. But the problem was that it wasn't using the classical resources very efficiently at all. And so there's still a lot of space on how do we take a big problem that's really hard and just get the quantum bits, the parts of it, to run on the quantum computer. I think that's the big challenge that everyone's exploring today.
So there's a classical optimization, for example, that happens after the quantum portion of it, right?
Correct, yeah. There's usually some sort of back and forth, and what is the right way to go to do this orchestration back and forth?
Yeah?
I would agree with the statement that we don't know yet, I guess, exactly, because what happened is that
I love that answer, by the way. That's what they need to hear.
What happened is that kind of companies and other people built first quantum computers, and then they wanted to run stuff on it and just created a software framework to run algorithms on these kind of standalone machines. And there are frameworks like whatever, Qiskit, Zerg, and others that have been used in the past. At the same time, HPC centers have their way of doing things, right? And these two, I don't think they go together very well. And this is now, I think, one of the tasks that we have to find out is like how to bring this together. Then all of the things that have been done so far have been mainly without any error correction layers. And I guess this is now kind of adding still like some changes to the way we think about the stack also on the software side. So I think it might sound maybe a bit desperate that I say we don't know, but I think it's also a huge opportunity because it actually shows we still have a lot of stuff in our hands to shape it and make it right.
And it does mean that you have actually recognized the problem, right? And you were working on it. Right? As opposed to it being an aha moment, right, at some point. And I'm sure you're getting to be good friends with the folks at Lumi, right? I mean,
exactly. Yeah.
You know, elsewhere in Finland.
Yeah, maybe I could just give an example of the thing we would like to do next. We had a research project on what are called embedding methods. So this is the classical chemistry approach. You have some large, complex system, and you decide which bit of the system you were going to run with one type of method and what kind of method are you going to run on another part of the system. So for example, you might approximate the water molecules that surround a protein with a classical simulation. Ignore all of the quantum effects and then use a more detailed quantum model for the protein itself. So this is a well-established approach in computational chemistry. And of course, the natural thing to do is say, well, why don't we just extend that? And there's a region of, let's say, this protein where we really want to apply the quantum computer. And so we've done that with a regular computer just to test it out. And I think this would be a classic thing to go try out on a HPC system. And it's interesting because essentially what you do is you solve the problem. You're kind of going back and forward between these different methods. So you solve for an effective Hamiltonian for the water. That then informs the Hamiltonian for the inner protein, and that then informs the Hamiltonian for the quantum computer. Then you go solve the problem on the quantum computer, and then you go back up. And you kind of back and forward, back between this until it converges. So I think this would be a really nice demonstration of kind of quantum computers and HPC working together on a problem that would be well suited to future utility scale quantum.
So for the last topic, and we just have a couple of minutes, so I just want you to touch on it. Some quantum computers, at least at the moment, are more amenable to being on-premise. Others are planned to be the size of a football field or 2 or 3. Not so much on-prem, right, unless you happen to be a football club, right? To do this. How do you eventually see this interaction? You know, that is, the quantum computer is just not local, cannot be local, or you may choose not to be local. So I just want, again, it's an integration question because I don't want people always to imagine that they're right next to each other. So just Alan, briefly, how do you think about this?
Yeah, I think this is actually an area that we don't talk about, which is cost. And for example, superconducting qubits is a fairly dense version of a quantum computer compared to the other modalities. And if you just look at the costs using our current technologies like coaxial cables or those beautiful chandeliers with all those little components in there, to make a 1,000,000 qubit quantum computer at the utility scale, it's an order of tens of billions. Mm-hmm. Nobody wants to hear that. And we have to figure out how to like drastically reduce these costs dramatically. And that's happened in the semiconductor industry. They call them integrated circuits. If we were to do an NVIDIA Blackwell machine today with these discrete components, it would take 600,000 kilometers of wiring, right? So we've solved a lot of those problems to bring down a lot of those costs in the semi industry, and I think it's imperative that we bring that over to quantum as quickly as possible. So that's my position on it.
Okay.
Yeah, I would echo this and maybe pick up on some of the things Steve and Alan have both said. I think we're currently going through this co-design phase, this testing and evaluation of how we integrate components together. And ultimately, we have to get that cost down because that will determine feasibility and viability of the technology, regardless of how amazing it really is.
Jan, and you'll have both. You'll have cloud and on-prem, and do.
Yeah, and I think the question is where does it balance out? And you can read different reports with different numbers, but in the end, I think you will always have both. There's a need for both, and we are convinced to do this. And I think we will manage to bring the costs down, to bring the size, the physical size down. All of this is already happening as we speak.
Okay, last words, Stu?
Yeah, no, totally agree. I think cost and power consumption. So what's the power plant that's solving all of this problem? I think that's really key.
Okay, thank you. Fascinating. Please join me in thanking the panelists.